The broadcast is now starting. All attendees are in listen-only mode.
Say something and then click back.
Huh?
Like, use the clicker to go up and down.
Okay. Testing, 1, 2, 3. Clicker works fine. Laser pointer works fine too.
Looks good.
This is what I was saying.
Welcome. I'm Ed Bogish. I'm the Executive Director of Syracuse COE. We're New York State's Center of Excellence in Environmental and Energy Systems. It's my pleasure to welcome everyone here in the room at Syracuse COE to our January Research and Technology Forum. And we also have a significant presence of folks who are tuning in via webinar. We actually have more people on the web than we have in the room, and we have a great crowd here in the room. The web attendees are from across the country. Lots of friends and collaborators from national labs and companies and others, and we welcome you all. You should know, if you're on the web, that you have a voice in the room here, and if you have questions, you enter them in the chat box, and we're monitoring the chat box, and those questions will be relayed to the speakers. This R&T forum is part of our partner program. If your firm or institution isn't already part of our partner program, I encourage you to contact Tammy Rosanio and learn all the benefits of our partner program. I also acknowledge with respect the Onondaga Nation firekeepers of the Haudenosaunee, the indigenous peoples on whose ancestral land Syracuse University now stands. We're pleased to be part of Syracuse University and to recognize the Haudenosaunee. I'm going to give a short introduction of our speakers. Ian Shapiro is a person probably who needs no introduction for the folks in the room, but there are people on the web, so I have to give Ian a proper introduction. Ian's a great friend and collaborator of Syracuse COE. He's the founder and chairman of Tatum Engineering in Ithaca. Ian was born in South Africa. He was raised in Westchester County. He got his bachelor's degree in mechanical engineering from McGill University and a master's from Columbia. And then he came to Syracuse and he worked for Carrier for 7 years or so. And then he had an itch to start his own company. And he started a company, Tatum Engineering, in 1989. So Tatum is celebrating its 30th year this year in December. So this will be like a victory year for 30 years. Tatum is an acronym. It's my favorite acronym of all time. Ian shared that he was influenced by a book called Small is Beautiful by E.F. Schumacher. And there's a subtitle of Small is Beautiful, Economics as If People Mattered. And Ian, when he started his company, named it Tatum, which stands for Technology as If the Earth Mattered. And Ian has been has led that company to be a well-established and well-respected firm that provides a range of engineering, design, and construction services. He's the co-author of books. One of his books is Green Building Illustrated, which I believe Ian wrote all the words, and all of the illustrations were by Francis Ching. So well-respected illustrator of books in the design community. So I think Wiley was looking for someone to match Ching and write the text for Green Building Illustrated. And they recruited Ian, and it's a terrific book. And then Ian has his own book, Energy Audits and Improvements for Commercial Buildings, another terrific book by Wiley. He has been a visiting lecturer at Cornell University, Tompkins, Cortland Community College, and Syracuse University. And again, a great collaborator of Syracuse COE. Evan Hallis, who will be joining Ian in giving this presentation, was born in Pittsburgh, raised in Ithaca, went to the University of Vermont, where he got a degree in environmental sciences. He returned to Ithaca and somehow found Ian. I think it involved a soccer ball. And Ian made him an offer. I guess this is like the recruiting to see if you could play soccer first, and then if you can, you're recruited to the Tatum team. Evan joined Tatum in December 2008. So just 10 years ago, celebrated his 10th anniversary. He's the manager of the Aeroseal services for Tatum. Evan has sealed ductwork in high rises throughout New York State and in New York City, including an operating hospital. He's leading a team for Tatum's participation in a Retrofit New York project in partnership with King & King Architects. It was recognized in 2014 by Home Energy Magazine as 30 under 30 folks to keep an eye on in the area of home energy. Ian and Evan gave this presentation at a NYSERDA Multifamily Summit in October, and I heard it there, and I asked them to give this command performance, encore performance of a presentation, which I'm sure will be of interest to folks from COE, and also our program that we call Tech Innovates, which is for manufacturers of products for thermal and environmental controls. We have a monthly program called Tech Tuesdays, and actually this is a Tech Tuesday. So we welcome our folks here who are part of that community. And now, without further ado, I'm going to turn it over, and this is going to be a tag team presentation by both Ian and Evan, and it's going to be terrific. So Ian and Evan.
Thank you so much.
So I know you don't like to be tethered, but by the mic will give the best experience for folks on the web.
Thank you so much, Ed. It's a treat to come here. This community has really become our community. I've learned so much working with Ed and many of the people in this room. And Hugh Henderson, I worked with at Carrier 30 years ago, and today is monitoring a new heat pump that's installed at my house as part of a NYSERDA project. It's just a treat. You can be very proud of what you've built here. We look to COE for just a place we come to share information. So, small package heat pumps, rethinking everything. I see us as going through a dramatic transformation of heating and cooling in New York State. Dramatic. What's happening right now, and in the next 5-10 years, is going to transform everything we do with heating and cooling buildings, and with energy use in buildings, and with carbon emissions. And we, in many ways, we're struggling with doing it right. And we're talking, it's all we talk about. Over 90% of my work has to do with heat pumps. How can we do it right in a cold climate? And the governor's goals, already several years old, the REV vision, 40% greenhouse gas emission reductions from 1990 by 2030, 600 tera-BTU in energy efficiency, so that's reducing energy use, and then complementing that 50% of electricity from renewable resources by 2030. So we're looking to reduce our use, and while we're reducing use, meet it with renewably generated electricity. In the last few weeks alone, these goals have been dramatically changed, and that 50% number as of today is 70%. Announcements in the governor's State of the Union, a big announcement in December and another one in January. 100% renewable by 2040. And part of that vision is to use that renewably generated electricity to eliminate fossil fuels, especially for heating buildings in a cold climate. So the governor is talking about technologies that support beneficial electrification. And every time I hear the words beneficial electrification or strategic electrification, I just translate it to heat pumps. Heat pumps for space heating, heat pumps for water heating, and even heat pumps for a lot of process needs. New York City's roadmap, they estimate that at least 60% of their space heating must be electrified, and we're talking heat pumps. Converting 60% of New York City's heating to heat pumps by 2050. And then a recent study by VEIC and NRDC, we're starting to see a lot of activity by NRDC, so the large environmental organizations are joining us. This is a national consensus towards heat pumps. And they perceive that 2/3 of all households could be converted to air source heat pumps. And today we're talking air source heat pumps. You know, in the mix very much is ground source heat pumps, which are used in this building and are really the Cadillac, the high efficiency option. So I feel somewhat agnostic. We do a lot of work with air source heat pumps. We also do work with ground source heat pumps. There's an interesting discussion about the relative merits of both. And today's discussion does not imply a bias to air source heat pumps. Before I start, this project was an initiative of NYSERDA's. And so NYSERDA asked us to look at package terminal heat pumps and small package heat pumps in general as part of a major initiative. So credit to NYSERDA for this particular study. It has just been posted, I think, as of yesterday. So our formal study, of which this is a short synthesis, is now online, and we're happy to share that. So the good news is that we have highly efficient air source heat pumps and ground source heat pumps already developed, and all we need to do is start using them.
Not so fast, Ian. So Ian's talking about these air source heat pumps, these multi-split heat pumps that we see in typical single-family homes, and he's right that we've made a lot of big strides in the last 5 years to be able to install and operate these split systems in our climate where we have really cold temperatures and still be able to meet our heating loads. But we don't just have small single-family homes; we have big buildings, and we have to come up with solutions for big buildings. And I don't know about you guys, but the building owners that I know are not going to do this to their buildings. This is not acceptable, I think, here in New York State. I mean, there's other areas where clearly this has been allowed and people are comfortable with it, but I don't think that we're going to see this here. So unfortunately, I think we still have a big challenge to overcome here. So I'm hoping that we can continue to push the industry to figure that out.
Oh, but Evan, you're just not aware of the latest technology. Have you heard about VRF systems? Look at these clean VRF systems up on the roof of a building, out of sight, significant capacity, cleanly installed, all kinds of indoor units, wall-mounted, floor-mounted, recessed. I think we're there. I think we're done. I think we just need to start installing.
Ian. I know that you're all about the heat pumps here, and you really think we've made it, but I'm working on a project right now where we're doing some energy consulting, and they are using VRFs, and that's great. However, in this one project, they've got 38,000 linear feet of copper piping to install that heat pump system. That's a lot of piping, that's a lot of refrigerant, that's a lot of cost to go into this one project. And if we're really going to be able to solve these problems, we need to be bringing the cost down and simplifying the solution. This is a new building, so it's a little bit easier to install this piping. But imagine trying to retrofit some of these buildings that we need to retrofit to meet our goals here. We're not going to be able to do it with all this refrigerant piping. But I did hear about one technology that we currently have called a package terminal heat pump. I think this is what you were mentioning before. We did our study on it. It's simple. It slides right in through the wall. You can do heating. You can do cooling. It does heating and a heat pump mode. What's the problem? Why can't we just use these package terminal heat pumps?
Oh, whatever. This whole routine was his idea. Oh, whatever. I worked on PTACs back when I was at Carrier in the 1980s. And PTAC heat pumps are, we found that they introduce air leakage into buildings. There was a fine study by Stephen Winter Associates. The average PTAC, so a PTAC is a small through-the-wall device, introduces 6 square inches of outside air as leakage into a building. And they're highly inefficient. Look at how dirty they get. And they use a lot of electric resistance backup heat. So I have serious concern about using a PTAC as the basis for a heat. So that's the end of our little routine, comedy routine. The bottom line is that with split system heat pumps, we're seeing superb developments in efficiency and in capacity, specifically with the variable speed compressors and with the controls. But we're struggling with cost. And what a small package terminal heat pump could offer, if they were efficient, is what we need most, which is affordability. we are really struggling with cost, installation costs, at a time when our energy costs are very low. Natural gas costs 1/2 of what it did 10 years ago. The new gas supply that we're seeing out of Pennsylvania and nationally, we've got a surplus of gas, the prices have plummeted, and it makes justifying heat pumps right when we need to do it most very hard to do. So, so the payback is difficult because the installed cost is high with split systems. What might be possible with a small package heat pump is affordability, if we can get it efficient. We need something that does both. And that was really the focus of our study. Heat pump pricing, we see everything, air source heat pumps, $15 to $30 a square foot. We see these numbers over and over and over. The larger systems, the VRF systems, easily at $30 a square foot. They're floating in the same range as ground source heat pumps, which are even more efficient. With tremendous features, good zone control, noise is excellent. Smaller split systems may be down to $15 a square foot. But what packaged terminal heat pumps could offer is $6 to $10 a square foot, a fraction of the cost. And this is the reason why these have seen widespread use, especially in hotels, but increasing use, surprising, in multifamily buildings. So if we had a small packaged heat pump that were efficient, what else would it give us? We don't need a mechanical contractor, or at least a licensed refrigeration technician, because it's a sealed product. It could be installed by a general contractor, by an electrician. Potentially fewer issues relating to refrigerants. It's a factory charge system, factory sealed. The chances of leaks happening due to field connections are much lower. Easy to service, one of the big selling points. Ed told me about the history of PTACs. PTACs were developed right in upstate New York. And their big selling point for 5-6 decades is that if one goes down, you pull it out, you take it down to your shop in the basement, and you slide in a spare unit. You've lost heat for all of half an hour. And so servicing on PTACs is tremendous, especially in the high-rise building. You're not losing heat to the whole building, you're losing heat for a short period of time. For developers, especially, again, multifamily buildings, but also commercial buildings, you can put the energy costs, heating and cooling, are now paid with the tenant meter. Fewer issues around ASHRAE Standard 15. ASHRAE Standard 15 has to do with refrigeration and refrigerants specifically. There are limitations as to how large a room can be that might be exposed to a large quantity of refrigerant. The concern is if there's a leak in that room and all the refrigerant leaks into that room, it will displace the oxygen. And so we've got limitations, and small packaged equipment get us around those limitations. Issues around refrigerants and heat pumps are going to become bigger and bigger. Refrigerants and refrigerant management is named as the #1 potential for reducing carbon emissions. We're at great risk with carbon emissions due to refrigerant leaks. And so maybe this nudges us in a better direction with refrigerants. So the promise here is not only cost, it's also service. It's also convenience of installation. there's several promises here with packaged terminal heat pump if we can get the efficiency. NYSERDA, recognizing this, introduced a innovation challenge around packaged terminal heat pump last spring. And here are some of the findings that came out of our study. Over 250,000 PTACs and packaged terminal heat pumps in New York City alone. Over 100,000 electrically heated PTACs and packaged terminal heat pumps. PTACs come in different flavors. There's the heat pump version, which is increasingly popular. There's a PTAC, which is just an air conditioner with electric resistance heat. And then there are versions that use steam or hot water coils for the heat. So they come in different flavors. Over 100,000 electric versions in New York State, outside of New York City. And one of our big surprises, PTACs are taking on in new construction in multifamily buildings in New York City. And I'm not talking about affordable. I'm talking fancy, market rate, high-end multifamily in New York. Taking off. Over a quarter of NYSERDA's high-performance multifamily projects, new construction projects, are PTACs. So we think of PTACs as being something that's limited to like motels, and that's not the case. We're talking about, I think, 400,000 or 500,000 shipments a year. This is a product that's a significant portion of the new construction market. I mentioned it already, retrofit conditions are poor because of the low cost of natural gas. It's hard to justify heat pumps. And then the last very important consideration, it's self-evident, but we need to keep reminding ourselves, we are in a cold climate. If we look at the Department of Energy climate zones for the country, virtually all of New York State is in the DOE cold climate. And this impacts heat pump efficiency and it impacts heat pump capacity. Both are important. There's a perception that in our climate, in a cold climate, that heat pump can't hack it at low temperature and air sources. So major issue. Almost all of the state is in the cold climate. New York City and Long Island are actually on the edge of the cold climate. They're formerly in the DOE mixed humid climate. Significantly, much of the U.S. is in the cold climate zone. It's not just the Northeast, it's most of the Midwest. It's a significant portion of the West, at least until you get to Western Washington and Oregon. And then look how cold climate goes down the Rockies into Colorado, Utah, and Nevada. The cold climate makes up 40% of the U.S. And this is significant because that's where we need heat pumps to work, in cold climate.
So I'm going to talk a little bit about the technology research that we did for our study with NYSERDA. We kind of took a look at the existing technology. We kind of focused on packaged terminal heat pumps, and I'll talk a little bit about that technology and what we found, and then also some of the other technology that we took a quick pass at that is potentially promising and also encouraging, hopefully, to other manufacturers to start thinking about innovative solutions to this issue. So when we look at packaged terminal heat pumps specifically, the biggest issue is they actually don't operate as a heat pump when it gets cold out, which is where most of our load is in terms of heating. So there are folks who think they're putting in a heat pump, but it's actually not operating in a refrigeration cycle. It's actually going to a backup electric resistance heat during the times that you have the most load and are using the most energy. The rated COPs are high, but they're which a COP is coefficient of performance. It's an efficiency measurement. and they're high when you look at the product specs, but those are all done at warm test conditions, so 47 degrees Fahrenheit. So once again, that's not really the condition that we are going to be operating this equipment at. And that's an issue actually with how AHRI has their certification set up for package tunnel heat pumps. So maybe there's some work that we need to do there in developing a better certification for these types of products to get manufacturers to kind of push the limit a little bit more. They don't use variable speed compressors, and that's one of the biggest advancements that we've seen in specifically in air source heat pumps and being able to work in cold climates is the use of variable speed compressors and variable speed fans to cut back when needed, but then when it gets cold out to run faster so that we can still achieve the capacities that we need. And when we did our review of about 30 different heat pump manufacturers, there was only one, package tunnel heat pump manufacturers. There was only one manufacturer that was using a variable speed compressor, but they were actually shutting the heat pump off at 40 degrees Fahrenheit. So basically it wasn't really being used in heating anyways, so it kind of defeated the purpose of that in terms of the heating side. I mean, it still was operating on cooling, but today we'll focus on heating. So the excessive use of electric resistance heat was another big issue, and that is, I kind of mentioned before how we're shutting off the heat pump at about 40 degrees, but there are other reasons why electric resistance heat is being used, and I'll touch on that in the next slide or two. And then another aspect that we need to keep in mind, and this came up when we were doing our research, when we were talking with building owners as well as other consultants in the field, is lots of concerns about quality and noise. So these are more of a lower end product, or thought of as a lower end product. Some of the newer equipment that's out, it's gotten better. I did some inspections and I ran some of the equipment, and it's starting to make some strides in terms of the noise. Ian talked a little bit about the air leakage. So that's something we have to keep in mind, because if we want to see market adoption, we need to make sure that the occupants of the building and our clients are going to actually find these solutions acceptable, which we've seen on the air source heat pump side, the mini split side, split system heat pumps is actually the noise has come way down, and you can have an indoor head that you don't even notice is running, which is great. So basically, we found that because of all these issues, the existing offerings don't meet the needs of us as consultants and energy efficiency professionals, and the needs of our bigger community in order to meet the goals that we want to meet in terms of reducing greenhouse gas emissions and addressing climate change. So to dive in a little bit deeper in terms of some of the issues, the excessive use of electric resistance heat. So the big one is that they are switching, these heat pumps, these package tunnel heat pumps are switching from heat pump mode to an electric resistance heater at about 40 degrees Fahrenheit. There was 2 manufacturers that operated at slightly colder temperatures in heat pump mode, but for the most part, they all switched to electric resistance heat. Another thing is that they're actually using that electric resistance heater, which is over here on the side, during warm temperatures as well. So there's a few ways that happens. So when a user changes the set point on the thermostat, some manufacturers have it, if it's a 2-degree difference between the space temperature and the thermostat set point, they will kick on that electric resistance heater to try to bring that space up to temperature quickly. Some manufacturers, it was more like 4 degrees, but there's an issue there where you start to train the user of that heat pump to crank that thermostat up so they can feel that electric resistance heat come on and heat the place up slightly quicker than the heat pump. And it kind of goes against the whole theory that I've always told, building facility people, that if you crank the thermostat up, it's not going to get hotter quicker. Well, unfortunately, with these package tunnel heat pumps, it actually does, and so we're kind of training the user to do that and switch it to electric resistance heat and not operate in that efficient heat pump mode. During defrost, so I'll talk a little bit more about defrost later as one of the issues, but during defrost cycles, when the equipment goes into defrost, they run the electric resistance heater to maintain temperatures, and then also the manufacturers that did operate in heat pump mode at lower temperatures, so say down to 32 degrees Fahrenheit, they have something called, once they go below that temperature, they have a dead band before they turn the heat pump pump back on. So, and that's usually back up to 40 degrees Fahrenheit. So you might have one evening that it gets down to say 30 degrees, it switches to electric resistance heat, and then it gets warmer into the 30s or even high 30s the next day. But that unit will stay in electric resistance heating until it gets back over 40 degrees. So we found that they're even when they're supposed to be operating in heat pump mode, they aren't. And both Ian and I have been in hotels multiple times and played with the package on the heat pumps, and we found even when it seems like they should be in heat pump mode, they are oftentimes switching to electric resistance heat. So it's definitely a concern in terms of meeting the efficiency requirements that we want. A quick analysis that we did just in terms of the actual impact of that electric resistance heat. So a typical split system, you might see an annual COP of around 2.5 or 3. And just looking at the impact of switching off the heat pump at 40 degrees, not counting all the other reasons why electric resistance heat kicks on, that because of so much load is in that colder temperatures, that actually the COP of our existing PTHPs that are on the market, and our client, or actually in this case it was New York City where we did the analysis, is more like 1.3. So we're really not operating as a heat pump. It's more of an electric resistance heater for heating. So unfortunately, that's an issue that we've got to work on. And one of the things that we found through our research and just in our knowledge about how heat pumps work is the challenge of defrost. So what can happen is when the coil that's called the outdoor coil can be below the dew point temperature, and actually you can have ice build up on that coil when you're in heating mode. So the equipment needs to do what's called a defrost cycle and switch from heating actually to cooling to send heat from the indoor space to the outdoor space to melt that ice. And so there's only 2 manufacturers who are doing that. So that's the main reason why the manufacturers are switching off heat pump at 40 degrees, because they don't want to have to run a defrost cycle. So that's a major issue, and it seems to be something that manufacturers haven't really been willing to overcome. And then the other big part of it is that when you melt this ice, we now have water, and it's cold out. And what do we do with that water? And that is a huge issue. So in the summer, when you're in cooling, it's actually pretty easy to deal with that condensate water. Basically, PTHP, package on heat pumps, they just sling that water onto the coil and evaporate it outside. Because if that outdoor coil is hot, it's warm out, and they can just evaporate that extra water to the outdoors. Well, when you're in heating, you can't be throwing that water back on the coil because that coil is cold and it will freeze. In a retrofit situation, it's going to be really difficult to drain that water anywhere else, right? We don't want to drain it off the building. It's going to freeze. It's going to drip on whatever is below on the ground. And we have a really challenging time to drain it to an internal drain. Typically, we need to get to install these in an exterior wall. Typically, the bathrooms and the kitchens and all the plumbing is on the interior side of the building and not on that exterior wall. So getting that condensate to a proper drain is challenging. There are one manufacturer that does something called internal condensate removal, where they actually pump the condensate from outdoors to indoors to drip it onto the indoor heating unit and try to evaporate it inside. But we're really concerned is that's going to possibly introduce some contaminants from outdoor and also really raise the humidity in the space. So that is an interesting solution to the problem, but we don't think it's actually going to be the solution that we need to actually address this bigger issue.
There is some debate on the project team about precision. He has some concern.
I am concerned.
So there's just one manufacturer who's trying to do this.
There is one manufacturer who does it. They also say that you can't do it within 2 miles of a coastline because of issues with corrosion. So we actually, this project that we did, this research project on, it was focused New York State and a lot of New York City focused, and New York City is within 2 miles. So there are folks who I think have used that technology, and it's not been an issue. But there is, the manufacturer kind of backs away from any warranties and all that. So
There's only one manufacturer that does it. There's only one member of our project team that thinks it's a bad idea.
I think that maybe that there could be some advancement in that, in that technology. Maybe we could figure out a little bit better. There are concerns. I mean, I did speak with some folks who had worked with these units more than I had, and they said you're bringing in water that could be sitting in that outdoor pan, and you're dripping it on indoor flow. So there's some concerns around smells and stuff like that. But this is the critical issue, we think, about priming a package system like this that could go into an exterior wall. And so what we also found was, well, we've got P-taps, right? And we've got these basically 16-inch by 42-inch sleeves in our walls. But we also have other types of cooling systems that go through the wall. So we've got through-the-wall ACs, which are basically very similar, just a slightly smaller box. And actually, on our retrofit New York project that we're working on, the building that we've designed a net zero retrofit for, they actually had through-the-wall AC sleeves in their living room. We are going to be removing those because we're going to be going to a split system heat pump. But if there was a product that could have met our needs, maybe we could have slid a product right into that sleeve, and it could have actually helped meet our goals in terms of construction costs. We also have window ACs, and we also have buildings that don't have existing penetration. So this is very common in New York City. We've got a building on the left that's got through-the-wall AC sleeves all across the whole building. So we've got penetrations already. Now there's some work that would need to be done in terms of air sealing those penetrations and making sure whatever unit we put in there. But rather than running refrigerant pipe all throughout this large building, and there's not actually a whole lot of space on that roof for all the VRF systems, you could actually slide into these units into each room and potentially have a really, really cheap and easy retrofit if we can address the condensate, the defrost condensate. And then we have buildings who actually put ACs in windows. So why couldn't we just swap those out for heat pumps? And all those spaces now that might be heated with, say, a 1-pipe or a 2-pipe steam system, gas-fired boiler, oil-fired boiler, can now be a heat pump. So that's kind of what we're looking for here. And I know that there's also a lot of people who say, well, you can't put holes in our walls, right? So there are buildings in New York City, when they wanted air conditioning, they had no problem putting holes in their walls. So this is a building that's got a wide variety of different systems through their walls. They've got window ACs, they've got through-the-wall ACs, they've got some P-taps. So clearly, when the need is there, people will be willing to do it. And so we would just argue that we think that we could develop a solution as an industry that could help address our need to electrify heating. And I don't want to take, I know there might be some great architects in the room, but I think we could come up with a better solution than this, but that could still meet the needs of that we have. Going back to this slide, actually, there was a consultant that I spoke with, Bright Power in New York City. They're a great company down there, and I had spoken with them about when we were doing our research about some of their experience with package stone heat pumps, and they actually did a demo project with a building who had a P-tap sleeve, which was not big enough to fit an outdoor split system unit in, but they actually retrofitted that sleeve. They made it bigger, and they stuck the outdoor unit of an air source heat pump in that sleeve, and then they mounted the indoor unit on the wall in the apartment. Because the existing system was an electric resistance P-tap, and because of the electric costs in New York City, it was, $1,500, $2,000, $2,500 a year to heat. And so they actually did the retrofit and got really great savings, but there were concerns about having to do that for the whole building, to do all that facade work. They ran some numbers, and I think it was going to pay back, and they just haven't decided to take that on, not necessarily because of the cost, but there are some logistic concerns about doing that work, obviously, in New York City. So that's kind of like what some folks are thinking about is like, we have these split systems that are efficient. Why can't we just put them in a different box and slide them through the wall? And so we are starting to see some of that. So I'm going to go through some of the products that we did see. We didn't go as in depth with these, so I don't necessarily have as much detail, but I'll speak briefly on them. And we're hopeful that we can continue to see more products. So the simplest one is very similar to a package only heat pump, is a through-the-wall heat pump. Basically, it fits inside of an AC sleeve instead of a PPAC sleeve. And it's got all the same issues as a PTHP, and has a little bit even more of an issue with capacity and efficiency, and more of efficiency because the coil size is smaller. But there's another great example where if we could just package our existing split system into a smaller, simpler box, we could actually meet these efficiency requirements. There are VTAC, vertical air conditioners, and they are usually put in the corner of a room on an outdoor wall, and they can also be ducted, so you actually can serve more than one room with one unit. There is one manufacturer that's come out one that's got a variable speed compressor and can operate down to 0 degrees. I have yet to get out to do an inspection. They have some installed, I think, in Rochester. I do want to try to get out there, although it does sound like they still have some of those issues with bringing on the electric resistance, even when the heat pump could be operating, to try to bring spaces up to temperature super quickly. Also, I talked to another consultant that looked at this for a passive house project, and they actually put it in a box, and they did an air leakage test on it. And because the unit is connected to the outdoors and the unit inside is not sealed well, there was actually a substantial amount of air leakage within the unit. So while it's a potential, has good potential, it's not quite there yet. So I think that's getting closer though. There's these two really interesting products that we don't have a whole lot of information on. There's one called Yes, My Green Invention Wall Mount Mini Package System. Not even sure these really exist. I did speak with them, and they're more of a manufacturer that is rebranding equipment that's made in China, and they're slapping their name on it. We are tasked to try to do some more research into these, but basically it's a wall mount system that's got two 6-inch ducts that go through the wall. So you mount it on next to your wall. You don't even have a sleeve. You just duct in air through the unit, which the coils are actually all contained within the unit. So that's pretty interesting. And it's actually very similar to what this Powermatic Vision, which is the unit that's actually sold in the UK. Same concept where you have two 6-inch sleeves that go through the wall, and basically so that you can have that air access to coils on the inside. And they have something called a nebulizer for the condensate, which is similar to this idea of like how do we get rid of this condensate? And what this nebulizer does is it heats it up and blows it out of steam. But there are concerns about what are they using to do that? Is that the electric resistance? Are we just, creating more energy use there? And it's unclear also if that's being used during the heating season or if it's more for cooling when you're done with the cooling condensate. There's a product that was, or maybe still is in development by NREL called the EcoSnap. I think they just developed like one demo or a few demos. It's basically, you've got an indoor unit that's like your typical wall-mounted split system, and then your outdoor unit looks like a typical AC. And the idea is that you could just have one 3-inch hole where your refrigerant and your electrical go through, and you have two mounts, one on either side of the building. You just drop them on and you snap them together. And the idea is that you wouldn't need to charge this; that it would all be pre-charged, and you just snap the pieces together. So that's an interesting concept as well, to try to simplify this process of electrifying and moving to heat pumps. And then the last one I'll talk about is what some people refer to as magic boxes. which are basically heat pumps integrated into ERVs and HRVs. And basically, rather than having a filter media or a desiccant wheel that transfers heat or energy between the airstreams, they're actually using a heat pump to transfer heat from one airstream to the other airstream. So these units are actually only using, like, I think the minimum tear is an 8-inch duct to the outside, so you have one supply air duct and one exhaust air duct. So in this case, you could mount one of these, say, in each apartment or in each office space, and just have two ducts going outside, and then this would have indoor ductwork to the space that you want to serve. So that's another really exciting product. Both of these, this is, I forget what this one's called, Building Equinox is the other one. And so that's really great potential. They still do both have some issues with electric resistance, but I think they're trying to work on that. And these are a little bit more expensive, but maybe if you're serving multiple rooms, the cost can come down. You have, once again, it's a packaged unit, so you don't have these issues with running refrigerant throughout your whole building. You still do have the condensate issue. So in summary, we looked at all these products. There was a number that are exciting, but they all have some issues. Mainly, they're using a lot of electric resistance heat, so being heat pump mode all the time. Some of them are lower efficiency. Once again, the heat pump's not operating at full temperatures. Most are using variable speed compressors. There's actually very few that are. So, and since we've made such great strides there, it would be really great to start seeing some of that technology into the small package heat pump world. The defrost issue and dealing with that condensate is really key to addressing this. And then there's just limited experience with these, and specifically some of those that I talked about that I haven't even had a chance to look at. So it's going to be hard to convince a building owner, facilities managers to be switching to these systems. Pass it back off to Ian here.
Thank you. I saw a remarkable statistic, just going back a slide, talking about limited use of variable speed compressors. I saw a presentation a few months ago that talked about use of variable speed compressors in heat pumps by continent. And like Asia, or Far East Asia, the penetration of variable speed compressors in air source heat pumps is 100%. And Europe is like 80% or something. And the US is about on par with Africa at about 10 or 15%. Just to show you that we have fallen so far behind in technology when it comes to heat pumps. And we're like, I don't know, is the heat pump developed at Carrier?
I've heard people at Carrier say that.
So we really need to ask for and demand and expect and use variable speed compressors. That's the only way we're going to get rid of this electric resistance. Now, we've talked about the affordability. These packages come up, it's like $1,000 to buy them on that and install maybe a few $100 in rent. That's how much it costs to live on these. Can we make them efficient? Can we make them efficient? And I think our perception is it's a box and it's small and it's too small to make efficient. So we looked at how small that box is. The standard piece is 16 inches by 42 inches, and it's anywhere between 18 inches deep, in some cases 21 inches. I think they go up to maybe 24. That's what we have to work with. And I think there's a myth that they are too small to contain everything we need to be efficient. So we looked at how much volume is occupied by a typical split system heat pump. That's the outdoor unit plus the indoor unit. That's the compressor and the two heating stations. And the typical split system is 5 to 8 cubic feet of volume per ton of capacity. And packaged tunnel heat pumps are in fact much bigger. They're ranging from 7 to 16 cubic feet per ton, averaging 8. They are bigger than split systems. We have more real estate available because they're only serving one room. And so we would argue that there is plenty space available to get a nice 11 HSPF or 12 HSPF heat pump into a packaged tunnel. And in fact, what we really need are smaller packaged thermal heat pumps, because today their size range goes from about 5,000 or 6,000 BTUs to 15,000 BTUs. But buildings designed to today's energy code, you typically don't even need 6,000 BTUs per hour. And if it's a high performance building, like a passive house building, you may need 1,000 or 2,000 BTUs. So what we really need with packaged thermal heat pumps are smaller capacities, down below 5,000 BTU. We need, I guess, 1,000 to 2,000 BTU per hour and up. And we'll keep the 15,000 BTU. We'll use those for retrofit. But there is plenty of room to put in the high efficiency, large heat exchangers that we need with a variable speed compressor and get the same or better performance than a split system. So what's our vision for EV, for existing buildings? Getting to net zero, this is what we're trying to do, is what Evan is doing with King Architects on a demonstration just north of Syracuse. We're currently seeing costs in the $60 to $80 a square foot to take a building, an existing building, and make it net zero. That typically means removing the fossil fuels, putting in heat pumps, adding some insulation, and putting solar. That's what it takes. This is the Dutch energy sprung model. $60 to $80 a square foot. Evan's project with King and King, we're getting down even below that. We're getting down, I think, down into the maybe 40s. That's still a substantial investment. It's a lot of money. We need to bring that down by 50%, we believe, in order for it to happen at scale. And a small packaged heat pump could be the key to doing that. Instead of $10,000, $15,000, $20,000 per apartment per house, we're talking about under $10,000. To increase market penetration. So that's the vision for existing buildings, is a way to make this net zero or deep energy retrofits affordable. For new construction, again, we feel that small package heat pumps, like a packaged thermal heat pump, could save us $10 to $15 per square foot on construction costs. Net zero construction costs are estimated to cost just about the same amount more. So what does this mean? If we could make an efficient small package thermal heat pump, we could be building net zero buildings at no additional cost. We're saving so much on the heating and cooling, we can put that and invest it into the solar that we need and into the insulation that we need. The vision is buildings that don't cost any more if we could get an efficient package thermal heat pump. The green system, what is our, what are we asking for? A small package heat pump, whether it's a P-tank or whether it's one of the interesting concepts like wall hung with through the wall, any. No electric resistance heat. We're doing it today with split system heat pumps. We're doing it today in our climate with no electric resistance heat. We need the same thing from packaged operate as a heat pump down to minus 20 degrees with the cold front coming in this week. That's what we need. We need our heat pump to operate down at minus 20. Just like these split systems. Daikin came out with a minus 20. I think Mitsubishi has is minus 18, minus 20. That's what we need. We're not going to be able to convince people to get rid of fossil fuels unless we can keep the heat pumps down to minus 20. We need to meet or exceed split system heat pump efficiencies, which we believe is very possible with a heat pump. Low infiltration and low conductive losses. We've got solid research saying that through the wall package equipment currently designed introduces infiltration and has conductive loss through the sleeve. We need to reduce those. We need to thermally break them so that there's not that conduction. And we need to have standards that say they won't reach 6 square inches per unit. There currently are standards for infiltration. We need them to be better. And then dispose of condensate. In an ideal world, we'd like to dispose of condensate without that interior drain. I think we can probably live with the drain if we have to, because we're living with it with split system. We can live with it, but this would be a home run if we could get rid of the condensate, especially the defrost condensate in winter. If we could get rid of it without a drain, that would be a home run. And then, like I said earlier, I'd like to see capacity down to 1,500 BTUs per hour. That's what we're seeing for high performance buildings. And buildings designed to the 2016 New York State Energy Code are what we used to call high performance buildings. They're tight buildings. So we need smaller capacity. These are the specs that I would love to see manufacturers saying, let's do it. We think it's very possible. The promise is affordable electrification. Again, I can't emphasize that the governor's goals and nationwide what the goals are to electrify through the use of heat pumps for space heating. And this is a key to reducing carbon emissions. Maybe it's the key. It's what they're doing in the Netherlands with their Energy Farm program. Thousands of apartments electrified the heat pump, covered with solar, and they've eliminated fossil fuels. And that's the model that we are really. There's almost consensus on it. I'm hearing consensus of that. New York City, state government, and I'm sure that the governor's office, the NGOs, NRDC, we almost got consensus, the national level. This is what we're going to do. We're going to improve our building envelopes, we're going to change the heat pumps, and we're going to go with solar, wind, and hydro. That's how we're going to do this. Major thing. And we feel that small package heat pumps can be an absolute key in the area of affordability. Thank you. We're happy to.
So Carrie Marshall will raise her hand and let us know if we have questions from the web, but questions here in the room. You Anderson.
Hey, yeah. So there's something called the cold climate specification for heat pump for me, and so you guys are incorporating that in what you do.
Needs cold climate specification.
Right. Yeah.
Basically, NEEP is the Northeast Energy
Efficiency Partnership.
Sorry. When I get excited, So Hugh Henderson asked about, is NEEP a good basis? NEEP has a cold climate air source heat pump specification. It says that your capacity at 5 degrees has to be the same as your capacity at 47 degrees. The only way to do that is to rate it at 5 and then to artificially say that your 47 is the same. Because in fact, you can, your capacity and efficiency at 47 are going to be much higher. So they derated at 47 and they're locked in at 5 degrees. I love that spec. And yeah.
And just a comment on specification, when I was trying to figure out the COPs of all these different packaged thermal heat pumps, and I actually called AHRI and I was talking to manufacturers, and I actually had manufacturers tell me that because AHRI, which is an organization that basically certifies and creates the test standards for equipment, because they don't have a test standard that measures efficiency at lower temperatures for packaged thermal heat pumps, the manufacturers don't have an incentive to perform at those low temperatures because they can't set themselves apart from the industry, because that's what the industry looks toward. So because the packaged thermal heat pumps only have a 47-degree steady state test standard, the manufacturers aren't really kind of incentivized to look to better the speed. So that's actually an area where maybe that, some folks can start putting pressure on AHRI to develop standards for, a seasonal efficiency or a lower temperature test.
Well, and that's what the cold time specification
Exactly.
is doing.
Yeah.
And the other funny thing about PTACs is, so PTACs are rated by standard 15 or standards 15 or 16, I can't remember. So HSPF and ESCER don't even apply to a PTAC.
Right.
Just so I don't know if everybody knows that.
Kelly, you got questions from the ethers up there?
I don't have a question. I have a comment from John Shapiro, who is sharing with us that they currently have a local community initiative promoting proven heat pump technology for northern climates, as well as building envelope efficiency improvement. They have a workshop scheduled at Bishop Harrison Center this Thursday at 7 p.m. And there is a website he shared, heatsmartcny.org.
So the announcement, in case people on the internet did not hear, it's a workshop coming up in cold climate heat pumps in Syracuse by Heat Smart Central New York. It's this Thursday at what time?
Thursday at 7 p.m.
Thursday, 7 p.m.
Website heatsmartcny.org, and I'll share that with everybody on the webinar.
It'll be shared, and it's heatsmartcny.org. John was my first person I worked with on heat pumps in 1983 at Cary. A small community.
This might be more of a common question. One of your slides looking at the units that had very minimal through the wall, like 2 portholes and condensate drain. One of those you listed the condensate eliminator as a nebulizer. Was that their word for it or your word for it?
That was their word for it.
Okay, usually a nebulizer is an ultrasonic device that runs at a fairly low power. It generates a mist of small droplets instead of actually converting it all to vapor. So that might be what they're doing.
So instead of heating it, they maybe just, it's like a humidifier.
Well, they said separating every single molecule of water, they separated it very tiny drops, like a humidifier, yes. Blow it up that way. So having the drain to the inside of the house means it stays molten, nothing water. And then the nebulizer would sit it out at fairly low power.
No. I'm open to anything. I think ultimately we're probably going to drain to the interior. That's probably what's going to happen. But not to have to do it would be a home run. Yes.
Are you concerned about like molds and whatnot and other growth that might get into Legionella?
Well, no.
Of course, I'm saying if you're flowing system, you can't get to the interior.
It's one of
the plumbing is correct, but I'm just saying.
Legionella is really warmer temperatures. What we're talking about in heating here is really much, much lower temperature. I'm not worried about Legionella. I think Evan has a valid concern. You've got condensate that's lying in a pan that's exposed to the outdoors. What's going to get in there? And now it's being transported to be dripped on the indoor coil. I'm not that worried about it. Once it evaporates, it's distilled water. But I can see that it might be a concern. I think ultimately we're going to drain. You know, and it's not treated as an obstacle. Let's just say we got to do it. We're going to drain.
Yeah, so I guess one more question. You keep talking about the 6 square inches of leakage. So is most of that inside the unit itself? Or is it between the unit and the sleeve? Or
So
did they ever quantify where it was?
I can't remember. The study is at Urban Green's website. It was funded by Urban Green, and it's called "There Are Holes in Our Walls." It made the front page of the New York Times.
I think that's not inside the unit. I think that is between the unit and the sleeve, and between the sleeve and the wall. Okay. I think that's both of those connections. But there is concern about leakage within the unit.
Yeah.
I definitely tore some of these units apart, and they're not that air sealed. But that doesn't mean they can't be. And that's kind of the point here is that these are not. This isn't that difficult to do. It's just a matter of a manufacturer in the industry wanting it and seeing this as a solution.
Yeah. And I was going to make a point. There's an ASHRAE standard for leakage from air handlers already. Right. So you could easily have a leakage standard for a through the wall unit or PTAC.
We didn't touch on it here. A challenge and a decision to be made is whether to integrate ventilation. And PTACs today do, and they do it kind of nominally just so that the unit has a CFM rating that can satisfy ventilation code, and then the designer is done with ventilation. My experience is that they're leaky, those dampers are leaky, it's not controlled ventilation. If I had my druthers, I would say, let's not do ventilation in a small package heat pump. Let's treat it as a heating and cooling device, and the ventilation happens separately. That would be my preference. But I think ultimately the manufacturers are going to have a big decision to make.
You aren't going to sell more giving up.
You're not going to sell more of them. They're in there today.
For that,
we're probably going to continue it. Maybe there is some parameter put on it for controllability.
Ian and I did actually, we had a conversation about this. We talked about like maybe we could use phase change material or ceramic, some sort of ceramic core, and actually integrate like an HRV into the PTAC. And I think that there is potential for that. We've done a lot of work in multifamily, and that's kind of where this study was focused. And we still have the issue of exhaust then, and we don't want to depressurize the apartment. So we actually, that's kind of how we got to maybe it's better to keep ventilation separate as we move towards higher performing buildings. So we need to keep that separate.
So the Miniterra product takes its focus is ventilation, and it does heating and cooling. Oh, by the way, that happens to be something else we do, but their focus is ventilation. And I guess we just can't forget about ventilation. I mean, it's going to be something we'll have to deal with.
Ian, at the beginning of your talk, you did mention ground source heat pumps. And I know, of course, you're trying to get your installation cost down. A large part of ground source heat pump is the earth coupler. Have you looked at water source heat pumps? Were they common gas-fired boiler and chiller to neutralize that?
Yeah, I've struggled with those. We did a study on exactly that system for envelope-dominated buildings, meaning multifamily, single-family, and hotels. And we found that system is the worst for carbon emissions. When we compare ground source heat pumps, air source heat pumps, a conventional fossil fuel heating system with a chiller, to what you're talking about, which is a water source loop with a boiler and a tap. The worst of the four for carbon emissions was the boiler tower system. Why? Because it's not getting free heat from anywhere. Every unit of heat that goes into the building is paid for. It's either fossil fuels through the boiler, or it is the electricity for the heat pump. And unless the building has some sort of a core, an air conditioning block, that's a source of free heat. But by definition, for an envelope-dominated building like apartments and hotels, you don't have a core. And so I'm worried that in our drive to do heat pumps, we're going to be doing, we're going to end up with some boiler tower systems, and I don't think they're good for, you know.
I don't like towers either, but I was thinking of air coupled
With a chiller?
with a chiller,
Yeah.
yes.
I'm not there. I'm worried about it. We're not getting free heat from anyone. We're paying for everything. And ultimately, if you look at a building that's a boiler tower heat pump, even with a chiller, either way, you're looking at a building that's partially heated with fossil fuels and partially heated with electric resistance heat. The heat pumps don't get you anything in our climate if there's no core, if there's no source of heat. It's complicated. I have knocked down, drag out fights with colleagues who, I had one last week, you know. I have a lot of fights in our office. Thermodynamically, it's very complicated. But the bottom line is I don't like it. Yes.
I was wondering if you could explain basically how the efficiencies are in the compressor, with the variable speed compressor. What are you getting?
The big thing is that
how does it work?
So it speeds up when it's warm outside. So it speeds up when it's cold outside. And so when it's not cold outside, like when it's 30 degrees, which isn't cold, it's operating super efficiently because the compressor's moving relatively slow. It only really speeds up when it's 0 degrees outside. It might hit its maximum speed at 0 or -10. So we're seeing tremendous efficiency at part low, which means anything other than below 0 is part low. And especially all of those hours around 20 to 30 to 40 degrees, where the packaged thermal heat pump is running like electric resistance. A nice split system heat pump, air source heat pump, or even the ground source, is running at part low. It's running, the compressor's running slowly, and it has thermodynamically, it's very efficient. And you can see it, you can see it. Test data will show you that it's running a COP of 3 or 4 or even 5 at those part low. And then down at the cold temperatures, the efficiency drops off.
Yeah, that's going to be another point, because what variable speed gets you with a heat pump is now, if you had a single speed heat pump, your COP isn't bad when it gets cold, but the capacity goes away. When you have a variable speed, you can go up to 90 hertz. It turns out that if you're at cold conditions at 90 hertz, that compressor doesn't draw as much power at 60 hertz. So the compressor can be at 90 hertz and still not be killing itself and drawing too much current, and you get more capacity. So that's, I think, I always say that there's two things. For air conditioning, there's part load thing. For heat pump, there's the part load, and you get higher capacity.
And the capacity.
Going to 90 hertz.
The capacity in our climate, we have to have variable speed compressor.
Yeah. And if you're efficient, but you only have this much heat, you're still not meeting the load.
Hugh has wonderful data on heat pump efficiency in the field, like real data, not the fake stuff. Very often what Hugh is finding is that a real air source heat pump is not hitting its annual COP of 3, but maybe it's 2 or less. And so we're learning from this field data that we have to follow best practices for sizing, for charging, or making sure there's good airflow, the airflow's not blocked. That, if we don't do that, we start operating at lower efficiency. It's a different topic. We are learning so much about heat pumps. I kid you not, there is so much we're learning, and it's not all good news. I mean, there's a lot of issues around air temperature, supply air temperatures, efficiency. Ground source heat pumps have a lot to be said for delivering efficiency and capacity. If we can put it together to invest in that welfare. Again, we're getting off on tangent, but the discussion that we're having right now is the discussion about how we're going to get off fossil fuels. Every one of these discussions about what happens at low temperatures and the efficiency and how we get rid of condensation, what it looks like and what it costs like and what it sounds like. These discussions are what are going to help our children get off fossil fuel. And so we have to have, I want to encourage you all, put heat pumps in your homes and wrestle with it. Because if we don't do it, it's bad news for our kids. Yeah.
Well, say, get away from fossil fuels. How are we going to manufacture these, and where's the electricity coming from? Because the sun doesn't always shine, it doesn't always blow, and how much land are you going to give up to put a bunch of solar panels in?
Well, getting to the governor's goals of 100% renewable by 2040 is no small feat. And in part, it will come by efficiency, insulating our buildings, reducing our use. In part, it's going to come from gigawatts that are off the coast of Long Island with wind turbines and that are not just as they have. If you fly over Scotland, you will see hundreds of wind turbines out in the middle of the ocean.
And how do you maintain them? I mean, obviously, there's elements. Seawater corrosion. I mean, these things are about 300 feet in the air.
Yeah, they are big devices that
and how much CO2 you're producing just to put install them in the first place? And to maintain them.
For sure, there's embodied energy, there's maintenance, there's reliability, for sure. Right now, we have countries like Portugal, Denmark, Scotland that have reached the days in which they are providing 100% of the electricity renewable. And we've got to
Germany had to use lignite coal back up when their green energy system didn't supply enough. They had to go back to lignite coal, which is more of a pollutant in the first place. So the point is, yes, I agree with you. We can be more efficient and we can reduce the amount of energy, but we're always going to need fossil fuels to create these things in the first place. And
what
derivatives to make them.
Yeah, the current vision is to try and reduce our space heating, our use of fossil fuel as much as possible. The current vision is that we will still be using fossil fuel for essential processes like industrial processes.
But you never hear that, though. That's good. See, I never hear the governor say that. The platitudes that come from the governor or any other politician, they don't even admit what you just said.
I think in advanced policy circles, I hear plenty of, we're trying to reduce it substantially. We recognize we're still going to be using some fossil fuels, especially for industrial processes.
Glad you said.
How are we doing for time then? Any questions?
No, just a thank you from John.
Hi, John.
So we have some refreshments outside for folks who are here at the COE. I'm going to say, why don't we take this moment to thank Ian and Evan.
I'm going to give you a heads up that our next Research and Technology Forum is going to be delivered by Tom King, who's here in the audience. And Tom's going to be talking about building envelope retrofits. So we look forward to Tom's presentation in about a month, and we can look forward to hearing that. In the meantime, again, thanks to Ian and Evan, and thanks to everybody who was with us on the web.